You ever wonder how your computer can just instantly find a word in a massive document? Or how a website knows, like, right away if you've typed a valid email address? I mean, it really feels like magic, but behind it all are some of the simplest, most elegant little machines you could ever imagine. Today, we're going to pull back that curtain and look at the hidden engines that really run the web.
Okay, so let's just dive right in. How does a machine, a thing that only thinks in ones and zeros, recognize something as abstract as a pattern? Whether it's finding the word cat in a huge wall of text or making sure a URL is formatted correctly, the computer needs a rock-solid, foolproof way to say, yep, this is a match, or nope, not even close. And the answer is, believe it or not, surprisingly simple and incredibly powerful.
So, here's our game plan for today. We're going to start with the basic rules of the game, what we even mean by language in this context. Then, we'll meet our pattern-matching hero, the automaton. After that, we'll see how to actually build them, how to combine them to make them even more powerful, and then the big reveal. We'll discover their one surprising secret weakness.
All right, first things first. Before a machine can find a pattern, we need a super precise way to describe what that pattern even is. And in computer science, we do this by defining the rules of what's called a formal language.
It all starts with something called an alphabet. Now, don't just think ABC here. An alphabet, for our purposes, is any collection of basic symbols. It could be binary digits, 0 and 1. It could be letters. It could even be a set of specific commands. These are our fundamental building blocks. So once we have our alphabets, our building blocks, we can then define a language. And a language is really just a specific set of words that we've decided are the valid ones, the ones we're interested in. It's basically the complete collection of all the patterns we want to be able to find. So, for example, our language could be all the words that end with the letter B.
All right, so we have our rules. Now we need a player. We need a machine that can actually read a word letter by letter and decide if it belongs to our special language or not. So let's meet the finite automaton. Think of it as a simple little machine that's built to play one game and one game only: pattern recognition.
Honestly, the absolute best way to think about an automaton is to picture a board game. At any given moment, you're on a specific square, and we call that a state. The word you're checking, the input, tells you which path to take to get to the next square, and the whole goal of the game is to finish reading the word and end up on a winning square.
So every single one of these machines is defined by just a few simple things. It's got a set of states. Those are the squares on our game board. It has one and only one start state. It's got at least one accepting state. Those are our winning squares. And finally, it has transitions, which are just the rules that say, hey, if you're on this square and you see this letter, you have to move to that square.
Let's look at a really simple example. This little machine here is designed to recognize one specific word, ab. We start at state 1. If the first letter we see is an A, we follow the path to state 2. Then, if the next letter is a B, we move to state 3, which you can see as a final, accepting state. If the word ends right there, bingo, it's accepted. Any other word, and this machine is going to fail.
Okay, time to put our little machine to the test. Let's try to feed it the word ABBA. Is it going to land on a winning square when it's done? Let's walk through it together and find out.
Okay, so we always begin at the start state, which is state 1. The first letter is A, so the rules tell us move to state 2. Easy enough. The next letter is B, which takes us from state 2 to state 3. Awesome, we're in a final state. But wait, hang on, we're not done with the word yet. The last letter is an A. We're sitting in state 3, and we look around. There's no path for A. The machine is stuck. It has nowhere to go. And because it can't finish, the word ABBA is rejected.
So we know how to use these machines, we know how to trace a word through them, but how do we actually build one from scratch? Let's take a look. It's really all about translating a simple idea into a map of states and transitions.
All right, here's a little challenge for you. Let's say our alphabet is A, B, and C. We want to design a machine that accepts any word, doesn't matter how long as it has at least one B somewhere inside it. Just take a second, think about the states you might need. What would be your winning condition?
So here's how a computer scientist would think about it. You actually only need 2 states: a waiting state, where we haven't seen a B yet, and a found it state. We start in waiting. As long as we keep seeing A's or C's, we just loop, we stay right in that same state. But the moment we see a B, boom, we jump over to the found it state, and we make that our accepting state. And of course, once we're there, we've already won. We can just stay in that winning state no matter what other letters come next. Pretty cool, right?
Now, this is where things get really powerful.
A single automaton on its own is pretty neat, but its true strength comes from the fact that we can combine them. We can snap them together to perform much more complex checks.
Think about when you create a new password. You might need one machine checking if it has at least one number and another machine checking for a special character. Well, using these operations, we can basically snap those two simple machines together like Lego bricks. We can create a single, more powerful machine that makes sure the password follows both rules. We can also connect them end-to-end to check for one pattern followed by another, or even flip a machine's logic on its head to accept everything except a certain pattern.
So at this point, these machines probably seem kind of unstoppable. I mean, they're the foundation for so much of our technology. But they have one fundamental, very important limitation. A secret weakness that defines exactly what they can, and more importantly, what they can't do.
This quote right here, this is the whole story. A finite automaton is a creature of the present. It knows what state it's in right now, but it has absolutely no memory of the path it took to get there. It doesn't remember the letter it saw 1 step ago or 10 steps ago. All it knows is, here I am.
And this lack of memory makes some seemingly simple patterns totally impossible for them to recognize. Take this language, for example. Any number of A's followed by the exact same number of B's. So words like AB, AABB, AABBB, they're all in the language. But ABB or AAB, nope, they're not. Let's just compare these two ideas side by side. Our little machine could easily check if a word ends in B. Why? Because all it needs to know is its current state based on the very last letter it saw. But to check for an equal number of A's and B's, well, the machine would have to read all the A's, count them, and then somehow remember that count while it reads all the B's to see if they match up. It just can't. It has no way to store that number. It has no memory, no little scratch pad to keep a tally. It fundamentally cannot count.
So the crucial point is this beautiful trade-off. The extreme simplicity of these machines, the fact that they're just states and transitions, is exactly what makes them so fast, so efficient, and so reliable. But that very same simplicity creates a hard boundary, a line in the sand for the kinds of problems they can solve.
So, what should you really take away from all this? Well, first, that finite autonoma are just simple machines made of states and rules, basically a game board. Second, they are the unsung heroes working behind the scenes in everyday tools like text search and compilers. And most importantly, their greatest strength is also their greatest weakness. They are incredibly powerful, but because of their simplicity, they fundamentally cannot count. And that really leaves us with a final thought. The journey from just a few simple rules about states and transitions all the way to the complex pattern matching that powers our digital world is, well, it's pretty astounding. And it makes you wonder, doesn't it? What other incredibly powerful systems are out there, built on foundations that are just as simple, hiding right under our noses?